Morning, everyone.
Morning.
Okay. All right. Hang on for 1 second here. Let me just. Fuck. I'll be right back. I gotta get a bottle for a light. Hold on. All right. All right. So I'm going to continue talking about chemistry of alcohols today, and we're going to cover substitution and then formation of sulfonate esters and displacement of those esters. So what's the question, Helen?
Yeah, do you have another group piece at this Friday?
Yeah, we do. Yeah.
Thanks.
So we're basically going to spend the whole lecture talking about alcohol substitution because this is actually very important transformation. You'll recall that if I take, for example, tert-butyl bromide and heat this up with water, in water, I can do an SN1 substitution of the bromide for hydroxyl. Okay, and one of the things that we said in the last class was, when we're thinking about dehydration of an alcohol, that's the reverse of hydration. The substitution of a bromide for water or for OH that is shown here can also be run in reverse. And so if I start with an alcohol with an excess of HBr, I can push the reaction back towards the bromide. Okay, and so the mechanism of that substitution, remember, principle of microscopic reversibility. We said that the dehydration, this video is still on here. The dehydration of an alcohol to an alkene is the exact same pathway as hydration of an alkene to an alcohol, but in reverse, it's the same thing here. So if I want to run this backwards, I can do that, but I got to follow the same exact pathway. So okay, so the first step would be protonation of the substrate. Second step would be ionization. And then the third step would be trapping of the cation by Br minus. So, okay. And so So if you take a tertiary alcohol and heat it with HBr, you can substitute that alcohol for the bromide. And key point is that OH is a terrible leaving group. To make it a good leaving group, we need to protonate. And it's the same thing that we saw with the dehydration, okay? You can also do this for primary and secondary alcohols, but it's still subject to the same SN1, SN2 sort of criteria. So primary alcohols are always going to go by an SN1, and secondary alcohols can break either way depending on the other substituents. So,
sorry if I missed it. What does excess stand for?
What excess, as in EXCESS? Yeah. Yeah, it's my sloppy abbreviation. So just give you an example for a primary alcohol. If you have, say, propanol, you treat that with HBr, okay? You can make the bromide, okay? But the mechanism will be different. It's not going to be an SN1 type of reaction because I have a primary substrate. So I will still protonate in the first step. Okay, but then there's no spontaneous ionization that occurs. The bromide comes in and does backside attack and displaces water. Well, and that gets you to the product directly. Okay, so you have a way basically to interconvert alkyl halides and alcohols now, right? So if we're starting with an alkyl halide, I can do a displacement with hydroxide, for example, if I'm not, if I want to do an SN2. If you want to do an SN1 type of pathway, if you have a tertiary substrate, you can think about water, just heating in water. And if you want to go from the alcohol back to the halide, you can heat with HX, HBr, HCl, HI, okay? And those reactions work, but here's the rub. The rub is that they're what we call very harsh. HCl is very strong acid. This is why these things are corrosive. And on a chemistry level, they aren't compatible with a whole lot of other things. Like HCl can just start to take apart a molecule. And so what we want is a way to do this transformation under more what we call milder conditions. And so that's what we're going to talk about with the sulfonate esters and some of these other reagents. Okay, so the HX substitution of ROH is effective, it works, but it requires very harsh conditions. Okay, and in synthetic chemistry, we always want mild. You always want something that's, room temperature, close to neutral, selective, gentle on the molecule. Okay, okay, so we want a milder way to take an alcohol to a halide. And I'll talk about two reagents and then sulfonate esters. And so the first one is a reagent known as thionyl chloride. So SOCl2. Okay. And this will take an alcohol to the corresponding chloride. The overall reaction is your alcohol plus SOCl2. typically going to add a base. The base that people will often use is this one here. This is pyridine. Okay. And I'll show you why in a second. And then that forms the chloride plus SO2 plus pyridinium hydrochloride. Okay. Does anyone know the pK of pyridinium salts? That compound on the right?
Is it close to neutral?
Close, about 5. Yeah, a little more acidic. Okay. So, yes, it's a good way to put it. It basically neutralizes the reaction. Okay, and so if you work out the mass balance without the pyridine, you've got an equivalent of HCl, and the pyridine basically buffers that. It reacts with the HCl, forms the pyridinium hydrochloride, makes the reaction more neutral. Okay, and that's what we want. All right, so what's the mechanism? And I'm going to draw this for a chiral alcohol because the stereochemical outcome needs to be minded. So if you start with an alcohol, say this guy, single enantiomer, I've drawn it with stereochemistry without the plus minus. That implies that I have a single enantiomer. I can have the alcohol attack, and the carbon sulfur or the chlorine sulfur bond is very weak. That is going to break, and so Cl minus is going to leave. Okay, and the immediate product then is going to look like this. Okay, so I've got my alcohol having attacked the SOCl2, and then chloride ion dissociated. Okay, I need to remove a proton from that alcohol now, and so what we're going to do is have pyridine come along and pick it up. So remember, pK of hydronium is about -2. This one has effectively an electron withdrawing group on it in the sulfur oxygen, so it's probably much lower. pK of the pyridinium is about 5, so that proton transfer is favorable. And that forms my neutral product, or my neutral intermediate. Plus, I'll draw the pyridinium on the side, plus Cl minus. Okay, and this is where the magic happens, so make sure you're sitting down. The chloride's going to come back in and attack. Okay, and what I'm going to do is break the CO bond, push that down to sulfur, and then break the sulfur chlorine bond and have that leave. And so that gives me my product plus SO2 plus the pyridinium chloride. Okay. So the conceptual thing that I want you to take away here is that, we're starting with an alcohol, and we said that's a terrible leaving group, right? And what I'm doing when I get to this point is I've basically converted my alcohol into a good leaving group. Okay. We describe this as like an activation. I'm activating the alcohol for a displacement. And so then I can have chloride come back in and do the displacement. All right. The second important point is that, if I were to tell you that, if we were to start with this compound here in the bottom center, and I just said, think of that SOCl linkage as just the whole thing's a good leaving group, right? And you had Cl minus react with it. It's secondary, so you'd have to think about it a little bit. But if we said, okay, let's just assume it's going to go purely SN2, you would say, okay, well, I know that's going to go with inversion, right? And it's the same thing here. This last step is an SN2 displacement. And so the stereochemistry, if there is chirality or there is an asymmetric stereocenter at the reacting carbon, it gets inverted in that last step. Okay. All right. So that's, so thionyl chloride is a nice way to take an alcohol to a chloride. If you want to do the bromide, thionyl bromide isn't really a reagent that you want to work with. Instead, we use triphenylphosphine dibromide.
Quick question. pH
Yeah.
in this is standing for like a phenyl group?
Yeah, sorry, pH is phenyl. So I'll draw out the whole structure of the reagent. So the 6-membered ring with the 3 double bonds, benzene ring, also known as a phenyl. When it's attached to something, it's a phenyl substituent. And so we can abbreviate that pH. Yep. All right, so that's the overall reaction. Alcohol, triphenylphosphine dibromide goes to the alkyl bromide plus triphenylphosphine oxide, which you haven't seen before, plus HBr. And so what's the mechanism? It's going to be very similar. Going to activate, going to displace. Okay, and so the first step is going to be attack of one of the alcohol at the phosphorus center. And I'm going to displace bromide. Okay, and so what I generate is this type of intermediate. So O, R, H plus, and I'm drawing the phosphorus with stereochemistry, so it's trigonal bipyramidal. You don't need to draw it with stereochemistry, but I think it just looks a little cleaner. And so we get that initial attack, displacement to bromide, and then there's an equilibrium, a proton transfer that's set up with the bromide. And I draw this specifically as an equilibrium because we know that HBr is a very strong acid. So this proton transfer is not going to go all the way to the right, but you're going to get a little bit of it occurring, and you'll form that type of intermediate, and that can dissociate a bromide. Okay. okay, and get to that ion pair. And so the reason this occurs, like, let me just explain this for a little bit. We're just having the bromide leave, which might seem unusual, but there's actually two things behind that. So one is that, three things behind it. So one is that phosphorus bromine bond is very weak. Second is that the phosphorus oxygen bond is very strong. And when you dissociate the bromide, you essentially make that phosphorus more electron deficient. It can interact more strongly with your oxygen, okay? And so there's sort of an enthalpic driving force. And then the third point is that this doesn't occur quantitatively. Again, this is, I should probably use reversible arrows. You get a little bit of this and then the reaction proceeds forward. And so at any rate, again, what we've basically done is taken ROH and then converted it into a superb leaving group, okay? And so now the bromide can come back in. Again, backside attack, if that's the stereocenter that's bearing the oxygen, it's going to get inverted. Okay, and so the net effect is that you get displacement of that activated phosphorus species with Br minus. Okay, so okay, and so in both of these instances, if you look at the structure I have circled at the bottom there, that's an intermediate. You can't really isolate that species. And it's the same thing for the thionyl chloride reaction. So that SOCl species is also a reactive intermediate, okay? And generally this is okay if you want Br minus or Cl minus to behave as your nucleophile. The question is though, is there a way that I could activate the alcohol, get some sort of stable activated intermediate, and then do a displacement with sort of a nucleophile of my choice? And that's where the sulfonate esters become important. So okay, so there are a couple different types of sulfonate esters that are used. I'll show you two of the most common ones. Okay, so this entire, all this gemisch on the right side is my leaving group, okay? And so the methyl group on the phenyl ring in a 1,4 relationship with the sulfur has a trivial name, and we call that a para-tol group. And so this is a para-toluene sulfonate ester, okay? And we can abbreviate that even further as just TS, or okay, and that stands for tosylate. Okay, so there's a couple different ways to describe these things, and so I can write this as CH3 TS, and that tells me that I've got that entire SO2 phenyl methyl group on there, okay? So this one's very common. Why is it common? You may be wondering. It's actually a byproduct. The sulfonyl chloride is a byproduct of saccharin production. So you take toluene, methylbenzene, and do an electrophilic sulfonation, and you get a mixture of isomers. And this is actually the undesired product. So it winds up being dirt cheap. And the other one that's useful to think about is the methane sulfonate. So this group right here is methane sulfonate. Again, we got abbreviations for these. We call these a mesylate or MS, okay? If I were in a competition and I had to choose, could only 50 reagents, I'd probably choose mesylates over tosolates. They're a lot more fun to work with. They're more reactive. They have some very nice properties about them. So it's my activating group of choice. And so we can abbreviate this. This would just be CH3, CH2O, MS for mesylate, all right? So how do we make these things? We can make them from the alcohol, and the general reaction scheme is going to be ROH plus, I'll show it for tosyl chloride. Plus some base, typically pyridine. And then that gives me my sulfonate ester. ROTS, okay? And so the mechanism involves, as a first step, attack of the alcohol on the paratoluene sulfonyl chloride, okay? So I'm going to attack the sulfur, kick out Cl minus, and what we form then is ROH plus, and then I've got SO the tosyl group plus the chloride anion, okay? And then in a second step, the pyridine comes along and deals with that proton. So bang, bang, and then that gets me to my product. Plus the pyridinium hydrochloride. Okay, so very simple. Again, this first step it looks odd. You're attacking sulfur, but it is an SN2 displacement just with an electrophile you haven't seen before. And the oxygens on sulfur are pretty small, and so sterically it's reasonable to have a nucleophile come in and attack. Okay. And so that's how you make the tosylate. And just to give you an idea of how good a leaving group it is, we can look at the pKa's of sulfonic acid derivatives and like say HCl, which we're familiar with. Yeah.
Could you go back a slide? Sorry, I think you're going a bit quickly.
Yeah.
Thank you.
Yeah. Yeah. So attack of oxygen of the alcohol, displacement of chloride gets you down to this guy, and then basically proton transfer to pyridine to get to the neutral product.
And sorry, what is the like second pathway that you have that like
This
the yeah.
just showing the byproduct is going to be the pyridinium HCl.
Oh, okay. Thank you.
We could just redraw it like this, you know.
Okay.
Yeah. Cool. So all right. So let's talk about pKa's. So just really quickly, water. What's the pKa of water?
14.
Yeah, about 15. And then pK of HCl.
-2.
Yeah, about -6. So we're pretty close with our sulfonate ester. So sulfonic acid, paratoluene sulfonic acid is -2.8. Okay. So remember when we said one way to think about leaving groups is to consider consider the pKa's of the conjugate acid of the leaving group. And if that pKa is less than 0, it's a good leaving group. If it's more than 0, it's a bad leaving group. And so the top would correspond to, water as a leaving group. This would correspond to hydroxide as a leaving group, tosylate as a leaving group, and then chloride as a leaving group. And we know that OH is a bad leaving group, but these two are good because the pK of the acid is less than 0. Okay, so I'm just basically the take-home message here is that when we form a sulfonate ester, we're converting the alcohol to a good leaving group that's stable. You can isolate these things, and then you can add another nucleophile and do a displacement. Okay, and so, for example, if you took an alkyl mesylate and reacted that with sodium acetate, we get our displacement to go. Okay, and we could form the acetate ester, right? The other thing too is don't let the sulfonate confuse you. So all it is a good leaving group. And we know that, another thing I can do with good leaving groups is eliminate them to make an olefin. And we can do that here. Again, you need to think, about the reaction parameters, but basically if you had cyclohexyl tosylate, and say I treated that with t-butoxide, okay, you can do the sort of elimination, the SN1 versus SN2, and then elimination versus substitution sort of assessment. Because it's secondary, I've got a bulky base, we're probably going to get a lot of E2 elimination, okay? And so you can eliminate that to make the alkene, right? And so the point is that the sulfonates allow alcohols to behave like halides, okay? And so the leaving groups that you guys know are halides, chlorine, bromine, iodine. Remember, fluoride is not a good leaving group. And then now these additional sulfonate esters, okay? And so why is this useful? So it's useful because we can do the displacement to get to other types of products. But it's also useful because the stereochemistry of sort of processing a sulfonate ester complements these thionyl chloride and triphenylphosphine dibromide reactions that we discussed. So spend a minute talking about that. So let me give you a hypothetical chiroalcohol here. Okay. So the game we're going to play is we're going to play a game called I'd like to substitute that alcohol. Okay. First question is, okay, I'm going to convert it to a sulfonate. Does the conversion to the sulfonate proceed with retention, inversion, or racemization of stereochemistry? Ghana.
Would it cause, sorry, the options were retention, inversion, and what was the last?
Racemization.
Okay.
Just the first step here. So do you guys know who Bob Barker is?
No.
No.
Oh my gosh.
Right guy?
He's Price is Right. Have you heard of Price is Right?
Yes.
Yes.
So I don't know who's the host now. Isn't it it's that comedian I don't particularly like. Is it Drew Carey maybe? But anyway, Bob Barker hosted Price is Right. I grew up watching Price is Right when I was homesick. Anyway, yeah, I don't have any prizes for you, but if you can guess this, you'll be in good shape for the exam. So let me help you out. So first step is retention. Nothing's happening with the alcohol. Okay. So we're going to sulfonate it. And if you go back to that mechanism on the other page, you know, all the business is occurring at the sulfur. So this proceeds with retention of stereochemistry. Okay. Now I'm going to bring in a nucleophile. So I told you we like the sulfonates because we can isolate them, put them in a bottle, and then I can react it with something else. Okay. And so the nucleophile I'm going to bring in is going to be sodium azide. Again, one of my absolute favorites. So I react sodium azide with the tosylate, retention, inversion, racemization, rosemary.
Inversion.
Yeah, inversion, excellent, because it's an SN2 displacement, right? And so backside attack, displace, SN2, inversion. Okay, and so the product that I have is this guy and 3 CH3. Okay, so the net result of this transformation is inversion of stereochemistry. Let me, come on, iPad. Okay. All right, that's interesting. So let's think about then what happens if I suppose I want to make that same alkyl azide, right? but I don't have access to the sulfonate esters, right? And so, okay, you say, all right, I gotta make the OH a good leaving group. I guess I'll try and react it with thionyl chloride. Okay, so retention, inversion, racemization, Izzy.
Retention.
Yeah, retention. No, sorry, inversion. So let me put it up here. Okay, so I'll just go back a couple slides here. So if I go back to my thionyl chloride on this slide, okay, we actually got the same alcohol. We're going to react it with the reagent. That's this first step here. And then there's a proton transfer from that addition product. And so I get to this compound in the bottom here. And what I've done is I've converted that alcohol to a good leaving group. Okay, and so now it's secondary carbon leaving group plus chloride, decent nucleophile. And so we can do an SN2 displacement. You're probably not going to do SN1 because it's secondary, and you're probably not going to eliminate because it's chloride. It's not a strong base. Okay, and so this step at the very bottom goes with inversion. And so then this initial step here goes with inversion. Does everyone follow me on that? Yeah, Caroline.
Yeah, so then would we then treat it with NaN3 after that?
Yeah, that's where I'm headed.
Okay.
So if we then say, okay, I want to treat this with sodium azide, right? You can say, what's the stereochemical outcome?
So then you'd have inversion again. So in effect, it would be retention as a whole, like for the whole. Okay.
Exactly. So you add the sodium azide, you displace the bromide, and you wind up with a second inversion. And an inversion of an inversion is a retention. Okay. And so the net effect here, is very strange. I'm the only guy on this call. I don't know where the other, I guess they all have it down and they don't need to be here. Double inversion gets you to retention. And so the point is that the important point, now I'm going to specifically put a question like this on the final. So congratulations, you're all going to be a leg up. The important point is that the stereochemistry of the product, we have the same product, right? Disalkyl azide, but now I can dial the stereochemistry depending on how I approach it. So if I sulfonate and then displace, it's a formal inversion of the alcohol. If I do my thionyl chloride reaction and then displace again, it's a double inversion. So it's a formal stereoretentive SN2 substitution. Okay. And so this type of, manipulation, this type of precision is very powerful, because we always want, when you have stereocenters, you always want to be able to control the stereochemistry. And now I'm telling you that if you can get me to one alcohol, I can get you either enantiomer of product. Okay. And so I'm not going to go through it, but I'd encourage you to think about this for the triphenylphosphine dibromide reaction, and then displacement, what ultimately happens you know, when you do that second displacement. So what's the stereochemical outcome there? Okay. All right. I will not miss Zoom. I'm sure you won't either. You know, say a couple words tomorrow, but it's been fun. When you're on Science Hill, feel free to stop by on the second floor of CRB. We'll do a normal problem set tomorrow, and then it'll basically just be the final. We're working on getting the exams graded. It should hopefully be done by the end of the day today, so you can email your TA and get your exam if you want. And yeah, we'll do you know, review sessions and things. I'm not going to do office hours today, but if you do want to meet, send me an email and we'll schedule a time. Okay, thank you.
So